Hello everyone, thank you for tuning in to another video. Oh, let me turn the light on because this is going to be really dark. While I do that, I'd like to remind everyone that the best way to use these to study primarily is to try them first by yourself, but then to watch these answers. So that being said, let's go into it. So two masses collide and stick together. As soon as you hear stick together, you have to think inelastic collision. Inelastic collision. Before the collision, one of the masses was at rest. Is there a situation in which kinetic energy is conserved? The answer is no. Good thing there's 3 yeses and 1 no. So that means I don't even need to read the options. It's done. Because if they stick together, it is what's called a perfectly inelastic collision. And in any inelastic collision, kinetic energy is not conserved. So the answer is D. Now, we're actually going to skip the second one. We're going to go through it after I'm done with the last 3 because the second one is probably the hardest problem in the entire packet. So we will adjust that in a second. So moving on to the third one, a 75 kilogram swimmer dives horizontally off a 500 kilogram raft. So raft, 500 kilogram, and then there's this dude, 75, jumps off, okay? The diver's speed immediately after leaving is 4 meters per second. A microsensor system attached to the edge of the raft measures the time interval during which the driver applies an impulse to the raft leaving the raft surface. The time is 0.2 seconds. What is the magnitude of the average horizontal force by the diver on the raft? Okay, so this is an explosion interaction. Basically, we have to think conservation of momentum, and we have to realize that this system started with no momentum. Originally, the guy was just sitting on the boat, and the boat was standing practically still, and so we say that there was no momentum initially. However, afterwards, the guy has momentum, and the boat has momentum. So let's label this M1v1 plus M2v2. Now, the guy has a mass of 75 kilograms, and his momentum is going to be, his speed is going to be 4 meters per second. Like that, okay? Now, that still has to equal 0, okay? And so the boat is going to essentially experience the same momentum. So, this momentum is the change for the one guy. We can add on the boat, but I'm realizing it's not really going to be that important for the problem. 700 kilograms, and it moves back with some speed. But we can figure out how fast the boat was moving back if that was important. But the whole point of this was to use the impulse equation. Force times time, okay? So they're asking for the average horizontal force, and we just need to find the guy's change in momentum. Well, it started as 0, and afterwards it's 75 times 4, which I believe is 300, which I was correct. So that means the guy started with an initial momentum of 0 and ended with a momentum of 300 kilogram meters per second. So impulse, represented by a J, is change in momentum. Change in momentum is final minus initial, so 300 minus 0. So 300 divided by the time of 0.2 seconds gives us the average force. 300 divided by 0.2 gives me 1,500 newtons. The answer is D for that one. You didn't even need to set up the whole momentum conservation equation. Number 4, or in this case, 24, 25, 26, 27, so number 27. The units of impulse are equivalent to which ones? Well, it's basically going to be the same as momentum. Just how work is the same, is joules, just like energy is. The impulse is basically the same thing, change in momentum, and so it's going to have the same units as momentum, which is kilogram meters per second. So that one's going to be option C. If the momentum of an object is tripled, its kinetic energy will change by what factor? So here's the thing. You have an object, its momentum is m times v. If you're changing an object's momentum, you're probably not changing its mass. So we're going to, in order to triple its momentum, we have to triple its velocity. So we would 3 times its v. That's how you would get 3 times the momentum. So 3mv, like that. If you did the same thing to kinetic energy, it would be a little bit different. So the kinetic energy equation is 1/2 mv squared. And so 1/2 m stays the same, but then you get 3 times the velocity squared. That 3 is also squared. So 3 squared is 9, so 9/2 mv squared is what it turns into, which is the same thing as what we started with, except with a 9 in front. So it's going to be 9 times bigger. So the answer is D, like that. Now, let's look at the hard problem. Two masses, M1, M2, with M1 equaling 3 M2. So mass 1 is 3 times bigger than mass 2. And I'm going to keep this relationship by saying that M1 is equal to 3M and M2 is equal to 1M. This allows me to cancel M's later on. Okay, so if the particles were approaching with speed v before the collision, so we've got two things coming together, each with speed v, heading toward each other like this. What are the with what speed are they moving apart after the collision? All right, so the key thing here is perfectly elastic collision, which means that we are going to not only have momentum conserved, Pi is equal to Pf, we will also have kinetic energy conserved. Kei equals Kef. So let's set up those really long equations. For mass 1, we're going to have 3m times v plus m times v. Now, you got to remember that it's a head-on collision. They're coming toward each other. So one will be moving in the positive direction, and one will be moving in the negative direction. So I'm going to change the momentum for this one to be negative. Okay, so adding negative or subtracting, whichever way you want to write that. And that should be equal to whatever they have after the collision. Now we know they should have the same mass because they bounce off of each other, they don't add together, but we don't know what this velocity is that the block 1 is going to have after the collision. So I'm going to say it is VF final 1 plus MVF final 2. All right, so that's the momentum. And let's try to simplify this before we move on. So 3mv minus mv is going to give me 2mv is equal to all of this stuff. And before I waste too much time, which I already have, let's cancel out the m's. And so basically this simplifies down to 2v is equal to 3vf1 plus vf2. And remember, the goal is we're trying to figure out what these two final velocities are compared to each other. So now let's set up the same equation, but for kinetic energy, because kinetic energy is also conserved. So 3mv plus 1/2 mv, both of these v's are squared. That's equal to 1/2 3mvf1 squared plus 1/2 mvf2 squared. Okay, so kinetic energy looks much more complicated, so let's simplify that right away. Everything's got a half in it, so let's cross those out. Everything's got an m in it, so let's cross those out. And we're left with this, 3v squared plus v squared is equal to vf1 squared plus vf2 squared. Oh, there's a 3 I forgot in there, 3. Now, some of you might be thinking, why isn't this one negative? Well, everything's squared, so a negative velocity wouldn't matter. And kinetic energy doesn't really matter what direction you're going, so there's no positive or negative. So negatives do matter with energy. Momentum, they don't matter with energy. So we can simplify this further. 3v squared plus v squared is 4v squared. That's equal to 3 vf1 squared plus 3v2 squared. Now, this is one of the reasons why it's the hardest problem. Whenever you set something up, set a problem up like this, and there might be one on the AP exam, but I don't think so. But even if there is, here's the trick. You take the momentum equation, that's much nicer, no squares, and you square it, you ruin it. So 2v squared gives you 4v squared. So 2v squaring the whole thing gives you 4v squared. Now we square this, so that means that each of these is going to be squared, so 3 squared is 9, vf1 squared plus VF2 squared. And you got to remember, this is a proper FOIL. It looks kind of something like this. 3F1 squared plus VF2. Squaring it means you multiply it by the same thing. And so you're going to have to FOIL this out. So this times this, 9VF1 squared plus 3VF1, 3VF1, VF2 plus VF2 squared. So that's what you get. Okay, so simplifying this down, 9VF1 squared plus 6VF1 VF2 by adding these two things together, plus VF2 squared. So you get this monster here, and this is basically what I wrote here, except I got to add on that 6VF1 VF2 thing. So this is looking awful, but it's for a reason. Now what we're going to do is we're going to take this guy and just subtract him. Since both parts of these equal sides, since both sides of the equal sign are equal, subtracting this from this side will be the same as subtracting this from this side. So let's do that. So let's minus 4v squared, and we'll minus this whole thing, 3vf1 squared plus v F2 squared. Okay, so if we subtract this energy part from the momentum part squared, we get 0 is equal to 6VF1 squared plus this subtracted gives you 0 plus 6VF1 VF2. All right, so if you're still with me, this is what we are left with. And it is nicer than what we had before, but it is a very complicated problem. But since it's equal to 0, we can do some pretty nice math tricks. So first thing I'm going to do is I'm going to divide both sides by 6. 0 divided by 6 gives me 0, and getting rid of the 6's over here. Very nice. Next thing I'm going to do is I'm going to divide both sides by VF1. So the final velocity for the first block after the collision. 0 divided by anything, still 0. And then we will have VF1 plus VF2 equals 0. Which basically means VF1 has to be equal to VF2, just different directions, just different by a negative sign. Okay, so all of that work, all of that math to realize that the speeds have to be equal for them. And if this is the case, that means that basically we're going to end up with the same velocity as we started with. V equals negative V, or in this case, this is going to be option D for this answer. How exactly I get that? We start with going back to the momentum equation we had all the way back up here. So 2v equals 3vf1 plus vf2. Now that I know this is true, I can replace this vf1 with a vf2. So 3vf1 is equal to negative vf2 plus vf2, 2v. So I can solve this out. Negative 3 plus 1 is negative 2. vf2 is 2v. Divide both sides by 2. And you get v is equal to negative vf2. Okay, and then obviously because of this, we get vf1 is also equal to positive v. Okay, so long problem. I'm not expecting them to ask you something like this, but it's important to know that during an elastic collision, both kinetic energy and momentum are conserved. So that's it for this video. I'll see you in the next one.